So one of the most important forms of energy to us as architects is this notion of heat energy, right? So heat energy is going to exist in a couple of forms that you guys are going to be sort of concerned with. It's going to exist as one form in molecular excitement. That is, a molecule, right, is vibrating or moving. So that's one way of thinking of it. The other one is as electromagnetic radiation in light. So that infrared that I was talking about. Okay? All right, so let's look at this notion of heat as molecular excitement. Okay? Isn't this exciting? Most items, right, even if they feel ice cold, contain energy. Okay? The more heat energy that's in them, right, the warmer generally that an object feels. The less, the cooler it feels. Now, that's not always the case, okay, because there's other factors involved here, such as conduction that takes place, and that has an impact on how you feel things. But you got to understand that everything you're going to come into contact with, right, has some form of heat energy in it. So let's think of heat energy as this little flame guy. And let's think of a molecule as this sphere, and the little lines show that it's vibrating. Right? See that right there? All right. So if we look at one object, and we can imagine it being a bar of metal, right? And this bar is made up of a grid of molecules. It's at room temperature, so it's kind of like this thing right here. Room temperature, I can touch it, right? And it contains a certain quantity of heat. And really, the quantity of heat would have been more in scaling these to a certain size and showing less vibration, but they all have it. Okay, but I'm just, again, this is just an analogy to try and kind of show you this notion of heat being contained in something. Okay, so imagine that this bar of metal, this is a little bar of metal, right? It contains 8 of these little heat dude things, right? So it has a certain amount of heat in it, correct? All right, now let's say I throw that thing in the freezer, right? And I get this thing down to the temperature of a bag of ice. So now it doesn't have as much heat energy, right? The heat energy got dissipated, got absorbed by the cold around it. So now it only has 5 of these these boogers. But it's now you touch it and it's cold, right? This is like Dumb and Dumber, where the guy sticks his tongue on the steel tube and gets stuck to it. And I don't know. He's stuck. Okay, so now imagine I take that sucker and I put it in the pan, right, next to those cupcakes we were talking about the other day. Now it gets hot. It gets oven hot, right? And now there's a bunch of these little heat dudes inside of that bar of metal. So think of heat as a substance that's in things. Okay? So the theoretical point at which there is no heat has never been achieved by humans. It's called absolute zero. And there's actually a video on it that's really trippy. I don't know if it's a Nat Geo video or something, but they're getting stuff down really cold. Okay? And it's weird what matter does when it gets down to almost absolute zero. They don't know what will happen to matter when it gets to absolute zero.
What starts happening to it?
Some stuff that would normally be a solid starts to become liquid or vapor. It does some weird stuff. I just kind of glanced through that video. It's called absolute zero. So it's kind of interesting. Okay? All right. So let's go on to electromagnetic radiation. So take a look at this. This is kind of a typical wavelength of sunlight, right? And you can see that the visible light constitutes a little more than a third, right, of what's inside of sunlight. How many of you guys have ever gotten a sunburn? Right? You can get a sunburn, right, from sunlight, and it's not from the visible light that you're seeing. It's from the invisible light called ultraviolet light. Okay? How many of you guys have ever opened up your hood and you just felt heat coming off the engine? Right? That is a form of infrared radiation. You can't see that heat coming off your engine, but you can feel it. Okay? All right. So heat is electromagnetic radiation. Most of all of the energy that exists on the face of this earth, right, has come here through sunlight. What makes plants grow? The sun, right? So they use carbon dioxide and they use sunlight through photosynthesis. And then the dinosaurs came along and munch. They ate all those plants. They died, turned into ooze. We put them in our race cars, right? So most of the energy that we come into contact on the face of this earth is coming from the sun, okay? One of the things that's important to note is that sunlight is constant, or for the most part constant, because when there are sunspots or when there's certain anomalies, there might be a little bit of differentiation, but there is this thing called the solar constant, right? And it's the amount of BTUs that are striking the outer surface of our atmosphere, not the Earth. The solar constant doesn't apply to Earth because it has to cross through the atmosphere. This is striking the outer surface of the atmosphere. And this is assuming that it's perpendicular to the rays of the sun. Okay? It's 429 BTUs per square foot per hour. All right? So one of the things that's really important is to try to understand the difference between heat and temperature. Okay? So heat and hot aren't the same thing.
Can you go back to the list like real quick?
No, because I've got to get this video finished. But this will be on the recorder so you guys can watch it. So heat energy is usually stored inside of something. Okay? Temperature is a measurement of how hot or cold something is, or how much heat, right, is coming off of that object. So here's an example. All right? So Mr. Bautista, I got a question for you. What contains more heat? An ice cube or an iceberg? Contains more heat. We already established that anything that has mass that we've ever come into contact with on this earth, right, has heat in it. So which one has more heat, the iceberg or the ice cube? The iceberg is much bigger. Ice has heat in it. The more ice you have, the more heat you have. Okay? All right, so heat compared to temperature, continuing on. The mass of an object has a lot to do with how much energy it's going to hold. Okay? So let's use an example. So a 2x4, there's some 2x4s over there, and a solid bar of steel. We don't have one. Okay? So think of those two things. Which one of those two things has more mass? Let me ask it a different way. Which one weighs more? The solid steel bar weighs a heck of a lot more than a piece of wood. Okay? All right. But I got to be careful because weight and mass are not the same. That bar of steel has a certain weight on Earth, right? But if we take it up into outer space, does it have any weight? But does it have mass? Yes, it has a certain amount of molecules of a certain size in it. Okay? So, wood member is much less dense, weighs less, and as such, it has a lower mass. The steel bar is probably heavy. Honestly, most of you couldn't pick that if you had a solid steel bar the size of a 2x4 by 8 foot long, most of you could not pick it up. James would probably pick it up. All right? So if we put equal amounts of energy into these things, right, different things are going to happen. All right? So you might think that you put so much energy into that piece of wood that it reaches 451 degrees. What happens at 451 degrees? It burns, right? Cellulose burns. But you could put that same amount of energy into that steel bar and you could probably still touch it. So there's a huge difference there, right? Let's talk about different ways to measure energy. So heat and hot aren't the same thing, and they're not measured the same way. Remember, heat, think of it as this substance that's in things, that's vibrating molecules. Temperature is how we relate to it. Okay? So heat energy is measured in either BTUs or joules, depending on whether you live in the most archaic nation in the world or the rest of the world. We still use the British thermal unit. The British don't even use it. All right? Hot and cold are relative temperatures measured in degrees. So heat is a quantity, right? Temperature is a relative scale measured in degrees. They're very, very different. Temperature didn't exist if it wasn't for humans. We made that scale up. All right? So here's the way that our scales, two of our scales came to be, right? So most of you have heard of Fahrenheit and Celsius, right? Both of them are related to water. Okay? So the first one was developed by this German physicist named Fahrenheit. Look when. This is slightly post-Renaissance is when he lived. Okay? It's a little after the Renaissance. Man, these guys were wearing some foo-foo stuff. This didn't even happen during the Industrial Revolution. The coldest that this guy could get something was by mixing ice and water, salt water, and he could get the temperature down to a certain point. Okay? And what he did is, and that point is way below 32. So he would get the temperature down as low as he could possibly get it. That became 0. So the temperature of a salt water frozen mixture becomes 0. That's not regular water. That is salt water. The point at which regular old water freezes, if that is 0, is at 32 degrees. And he picked this magic number out of the air. Half of the Earth's circumference in degrees is what? 180, right? Circle, half a circle. So he just picked 180 out of the air, right? And he said, all right, if the temperature of water, if I say that if the temperature of salt water frozen is 0, and the temperature of 180 added to that becomes the point at which water boils, then, hey, that becomes 212 degrees. Okay, it's arbitrary. He kind of picked things to kind of relate it to. And they're kind of weird things. Most of you are going, that sounds kind of strange. And I like it when it's 75 degrees outside. So this guy, this Swedish guy, Celsius, he comes along in the 1700s, right? Sort of contemporary to what's going on with Fahrenheit, but still, he's one of these guys that's dressed in some weird foo-foo stuff. He's not dressed like we are today, right? Think of him as wearing weird hats and stuff. And there's counts and kings and stuff like that around. He says, well, you know, this Fahrenheit guy, whatever, I think we should say that water, regular old water, freezes at 0 and it boils at 100. Conceptually, that makes more sense to me, right? So there's also another scale called Kelvin. We're not physicists. So we're not going to worry about Kelvin. Okay? So measures the temperature. Logically, the Kelvin scale makes a lot of sense to physicists because it runs upward from absolute 0. And what is absolute 0? No heat. Okay, so this is a theoretical construct. All right? So it's again, the point I'm trying to make with these is to show you that temperature is a man-made construct based on certain kind of things that we kind of observe in nature. All right, so we're going to stop at this point. I'm going to stop the recording because I'm almost to 15 minutes. Terumi.